Well, last time we were working on GCDs, and I talked about a definition, but I did not write it down, so I want to make sure that you get it in your notes. So the definition was this: let A and B be non-zero integers, then A and B are relatively prime, provided that the GCD of A and B is equal to 1. This is what we talked about where you're given two integers, and if the GCD of the two integers is 1, remember GCDs have to be positive, so this is the smallest positive integer possible. So when A and B have a GCD of 1, we call it relatively prime. Now with that, remember we also talked about Theorem 1.2. And Theorem 1.2 stated, given that the GCD of A and B is equal to D, then there exists integers U and V such that, and we got an equation, AU plus BV is equal to D. Now, so I'm going to kind of quote my own little theorem here using if they were relatively prime. So I'm going to call this guy Theorem 1.2b. And it's just a, so you'll see with the relatively prime. So given that the GCD of A and B is equal to 1, and then it's going to be then there exists integers U and V such that AU plus BV is equal to 1. Furthermore, if you have an equation with integers, of course, A times integer U plus B times integer V equals 1, then the GCD of A and B is equal to 1. And pretty much I'm doing this if and only if with Theorem 1.2b, and that's because 1 is the smallest positive integer. So we said, this idea, I was paraphrasing this one up here, given that the GCD of A and B equals D, then there exist, not necessarily unique integers U and V, such that AU plus BV equals D. But if you're going to set that guy equal to 1, that's the smallest positive integer that's possible. So if you ever come up with an equation like this, then the GCD of A and B is going to be 1, the GCD of A and V would be 1, the GCD of U and B would be 1, and the GCD of U and V would be 1. And it's the idea that 1 is the smallest positive integer. But when the GCD of A and B equals 1, we call A and B relatively prime. All right, so let's continue on with section 1.3. Definition. An integer p is said to be prime if p does not equal 0 or plus or minus 1, and the only divisors of p are plus or minus 0 and plus or minus 1. So what we're saying here about prime integers, they could be positive or they can be negative. Negative 3 is prime, just like positive 3 is prime. But you cannot be 0 or plus or minus 1. We do not consider 0 or plus or minus 1 prime. So if you're talking about prime integers, let's talk about positive prime integers. The smallest positive prime integer would actually be 2. Then you get 2, 3, 5, 7, 11, 17, 19, ... You keep on going forever. So note that if P is prime, if and only if negative P is prime. Also note that if P and Q are prime and P divides Q, the only way that can happen is then P has to be equal to either plus or minus Q. Theorem 1.5. Theorem 1.5 states that let P, B, and C be integers with P not equal to plus or minus 1. Then P is prime if and only if P has the property that whenever P divides a product B times C, then P either divides B or P divides C. So there's a property of primes that whenever I have a prime that divides a product, it either divides the first guy or it divides the second guy, or it could divide both of them for all we care. But that's an interesting property of primes because since primes can't really be factored, when P divides a product, it'll either divide the first term or it divide the second term. So with this one, I'm going to actually prove this one for you guys. Now, this one's a little bit more elaborate proof, so this gets more into our proof skills and stuff. It is this idea of if and only if. This is a two-way street, double-sided implication here. So if P is prime, then you'll have the property that whenever P does divide a product, then automatically you'll get that P divides B or P divides C. And it goes the other way. If P has the property P divides a product B times C, whenever that happens, you'll either have P has to divide B or P divides C, then that will actually force P to have to be prime. So how do you prove a double-sided inequality? Well, you're going to have to do it one step at a time. So this is a two-step proof here. So I'm going to put a little arrow like this. And I'm going to prove first the forward way. So with the forward way, we're going to suppose P is prime, the first part, P is prime. And we're going to give ourselves and let P divide B times C. Of course, all these guys are integers. You don't need to restate that. So let us look at the GCD of B, just one of the integers, and P. Okay, so remember, since P is prime, if we look at the GCD of just B and P, then only two things could possibly happen here. Then, either the GCD of P and B is going to be equal to 1, or the GCD of B and P would be equal to plus or minus P. I never actually stated P was positive, so but with the GCD, a GCD always has to be positive. Okay, I'll just put it in there. Always positive. Okay. Now, we're there. Basically, I just broke this into two cases. So we'll focus on the two cases here. So we'll do the easy case. Case number 1. If, I'll call this case number 1, if the GCD of P, B, and P is equal to plus or minus P, then we automatically know that P divides B. Now, how do we know that? Well, think about it. If the GCD of P and B is P, and P and this P plus or minus P is the greatest common divisor. It's a divisor. So if P and B are both divisible by P, well, clearly P divides P, but P also has to divide B just by definition alone of GCD. So, and we got basically P divides B. So we got what we wanted to show with case number 1. Now with case number 2, if the GCD of B and P is equal to 1, that means they're relatively prime. Now let's understand. We were given that B and given, I'll state it up here, P divides B times C. So we got GCD of B and P is 1 and P divides B times C. Well then, by theorem, I believe it was 1.4, P must divide C. We proved theorem 1.4 last time, and just to show you guys this, I pull out my little book here, see if you can see this. But there it is. This is what we proved last time in our notes. If A divides, now remember we're not allowed to use the divide symbol here, so if A divides B times C, then, and this is Dr. Hungerford, that little order pair means GCD, then and the GCD of A and B is 1, then A divides C. This is what we proved last time. So what I've got going on here is this. Okay. So therefore, we have either P divides B or P divides C. And I'm done with my forward way implication. Now, to do the if and only if, I'm going to give myself the second part of this guy and actually have to prove the first part. So I'm going to slide this up a little bit. Okay? Here we go. Okay, so on the second part, we're given this. Suppose, given that we have the property whenever P divides B times C, then P divides B or P divides C. And this means for all integers. Whenever we're given that P divides a product, P either divides the first guy or it's going to divide the second guy. Okay? And I'm going to do a technique of proof called proof by contradiction or proof by contrapositive. I'm going to assume the opposite of what I want to show. And then I'm going to show I'm going to get a contradiction, that can't happen. That's a proof by contradiction. The old, if P implies Q, that's equivalent to saying not Q implies not P. So I'm going to assume Okay? P is not prime. Okay? So here we go. With that, since P is not prime, there exists integers, and just give myself a couple integers, x and y, such that P is equal to x times y. So if it's not prime, these are integers and they're not going to be 1, they're going to be bigger than 1, such that P is equal to x times y. It factors. But remember what's given. Whenever P divides a product, and you always divide yourself, thus, when P divides a product, plus, well, let me put this and. I want to emphasize this. These guys would be smaller integers than P. So the absolute value of x would be strictly less than P, and the absolute value of y would be strictly less than P. Now P is equal to a product, and it factors, so x and y would actually be strictly smaller than P. Okay? But remember what we were stating here. We're given, since P divides a product, well, as P equals x times y, then P divides x times y. You're equal to yourself x times y times 1, so basically if you're equal to yourself, you can divide by yourself, and the ratio is going to be 1. So P divides x by 1, x times y. But by property, whenever P divides a product, it either divides the first guy or the second guy. So P divides x, or P divides y. Now let's think about it. X and y are strictly smaller than P. When you divide an integer, the integer you're dividing must be the same or bigger than you are. But x and y are actually smaller than P. So, and that's a contradiction. A contradiction. And the symbol for contradiction is two arrows basically facing each other oppositely there. So we have this, and therefore a contradiction, which means that what we assumed must be false. Therefore, what we assumed, which was P was not prime, is false. Therefore, P is prime. And that's what I wanted to show. And the secondary part up here was that, quote, I was given the second part, P divides a product, then P divides B or C, then you actually, going the other way, then P had to be prime. And that it pretty much ends up my proof for this guy. So you get a little flavor of the idea of a proof by contradiction. Now, just to let you guys know, when it comes to this stuff here and the like, we are going to sit there and when you're looking at these particular problems and stuff, we're not going to be doing much of the proof by contradiction. That's something I pull out on occasion. The focus on this course is this more direct proof. So all the proofs that I'm going to be doing are direct proofs using theorems and definitions and statements to logically conclude that what we were asserting is actually true. That's a direct proof. Now, when you get into your advanced calculus classes, Math 31, 41, and the like, when they start, especially in analysis classes, they love proof by contradiction. If you got a proof, because they're usually short and sweet. So assume the opposite of what you want to show with all the givens, and something false will actually show up and stuff. So with that, you will see a lot more of these things in your future. But for us, we're going to do more of the direct proof. All right, going on to the next problem. Trying to get all these things off the screen for you guys and stuff, because I got like 4 different computer components trying to get these recorded to you guys. All right, so here's the next one. Corollary 1.6. Remember what we talked about corollary. Corollary is a theorem that typically follows from the previous theorem. So with the previous theorem, we were talking about the idea that whenever P is prime, then P and P divides a product, then either P divides the first guy or P divides the second guy. It's one of these wonderful properties of primes. Now, Corollary 1.6 says this. If P is prime and P divides A1 times A2 times A3 times AN, a bunch of integers, P divides the product of a bunch of integers, then P divides at least one of these AIs. They may divide more than one, but it's guaranteed you're going to divide at least one of these AIs. And again, the proof of this one is done by induction. And I'll just kind of talk about it for you instead of writing it up. Now we've got Theorem 1.5 says that whenever P divides a product, P either has to divide the first guy or the second guy when P is prime. So what you do here is to use Theorem 1.5. You've got P is prime, and you've got P dividing a string of integers, A1 times A2 times A3 all the way up times AN. But you want to sit there and group them out like this. So you put little parentheses around. So now you focus on basically 2 things. Either A1 times the rest of them. So if P divides A1 times the rest of them, according to Theorem 1.5, then either P divides the first guy, A1, or P divides the rest of them. Well, if it doesn't divide A1, well then throw him out of the mix. Then you've got P dividing the rest of them. And then you keep doing the same trick, this induction step here. So if P divides A2 through AN, again, then you can sit there and group these guys together. Then according to Theorem 1.5, since P is prime, P either divides A2 or the rest of them. If it doesn't divide A2, throw it out, and it divides the rest of them. And you kind of march yourself down the line, and then by induction, you eventually are going to have P dividing at least one of these AIs. Okay? Now, then because of that, Theorem 1.7, and it brings up another major aspect of calculus here, algebra is what we call it. Theorem 1.7, every integer n except 0 and plus or minus 1 is a product of primes. Now this is something that we were taught in elementary school, honestly, that prime factorization and the like. And so every integer can be written as a product of primes. So with that, we have what we call the Theorem 1.8, and you know you're in trouble when they start calling the words fundamental theorem. So we have the fundamental theorem of arithmetic. And I didn't type this one up for you guys. I thought I would actually write this one up for you guys. But it pretty much says this. Every integer n except 0, 1 is a product of primes. Connects back to the last theorem. Okay? Every integer n except 0 and plus or minus 1 is a product of primes. And here's a little bit more. This prime factorization is unique in the following sense. if n is equal to P1 times P2 dot 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 time all the way up to PR, and if you take this in, it's also equal to Q1, Q2 dot 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 out to QS, with each PI and QJ are prime integers. Then here comes that idea of uniqueness. Then R is equal to S. So we have two different products here, but R would actually be equal to S after reordering. And after reordering, P1 would be equal to, because they're prime, plus or minus, we have the positive or negative prime, Q1. P2 would be equal to plus or minus Q2. Again, if you reorder, so if you think about it, typically in high school and junior high school, when we were actually talking about being a product of primes, we usually either did this product from low to high or from high to low, and that makes the order unique. So P3 would be equal to plus or minus Q3, and then dot, 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 PR would be equal to plus or minus QR. Okay? And again, the proof is actually in your books. You can actually look at the proof, check out the book, and it's a induction style proof because this is more of a formula type of thing here. But this fundamental theorem of arithmetic goes back to what we learned back in junior high school about every integer can be written as a product of prime, and this product is going to be unique up to order, and typically with that order we go from low to high with your prime factors and stuff. So in connection with that, we have our corollary 1.9 with this. Every integer n greater than 1 can be written in one and only one way, in the form n equals P1, P2, P3, dot, 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 PR, where the P little t's are positive prime integers, such that P1 is less or equal to P2, which is less or equal to P3, dot, 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 less or equal to PR. That unique order is, this will be the smallest prime, and then the next smallest all the way up. And when you write it like that, this representation is going to be unique. That's what corollary 1.9 is saying. And traditionally, if we're talking about positive primes, then we don't have to worry about the negatives, and the first one being negative, but the next one's going to be positive. If we just focus on the positive integers, n is greater than 1, positive integers, then this prime factorization is going to be unique. And we traditionally write it from low to high. Now, the next thing I want to discuss with you guys is I wanted to look at some book problems for you. So let me slide this thing up. You guys can see a little better on my little makeshift table that I got going on here with this stuff. And I just want to kind of grab the book over here, and I'm going to focus on a particular couple of problems out of the book and talk about, actually proving these guys. And the first one I'm going to do, really pulling the book over here, and it's problem number 17. And this is not really a proof. This one is a question. If P is prime, and remember this is Dr. Hungerford's book, that little order of pair means GCD. So if P is prime and the GCD of A and B is P, then what do you think the GCD of A squared and B squared are going to be? Okay? So basically you're filling in the blank here. So this is not a proof. So I kind of want to get into this idea of, ideas and stuff like that. So I'm pulling my table down here. here we go. So this is problem number 17. All right. So we were given the GCD of A and B are integers, is equal to P. Okay? Pretty much if the GCD of A and B is equal to P, then what do we think of what's going to happen for the GCD of A squared and B squared? What would that be equal to? All right. Now, this is more of a scrap sheet of paper, and this is what I want to talk to you guys about. When I'm doing actual proofs, I typically start out with a scrap sheet of paper, and I write down all the things that we know. Okay? And so I'm trying to formulate my ideas. Now, this is the sheet that I never actually showed, and this is basically what I want to show here. I'm going to use the famous WTS. Want to show. I want to show that the GCD of A squared and B squared would be equal to what? Now, first off, you got to have an idea. Then I'm talking about how to prove this thing. Well, if the GCD of A and B is equal to P, then the GCD of A squared and B squared, I think, is going to be equal to P squared. But that's just an idea. I'm guessing. So this is basically what I want to show. So I'm going to start with, want to show this idea. You always start yourself with a given. So this is not a proof. This is basically a formula page of collecting my thoughts. So I'm given that the GCD of A and B is equal to P. And on my scrap sheet of paper, I can write all kinds of symbols I want to. What does that actually mean? Well, just from the GCD and focusing on the D part, if the GCD of A and B equals P, that means that P divides A and P divides B. Oh, that's right. I'm using the little divide symbol. That's all right. I'm not turning this thing in. I'm just formulating what I'm going to be writing down. That's P divides B there. So, all right. So what does that mean? Okay. Well, that implies, keep on going with my implication here, if P divides A and P divides B, that does mean that P squared would divide A squared, and P squared would divide B squared. So I know that P squared is going to be a common divisor of A squared and B squared. So I've got the first part if I wanted to show that the GCD of A squared and B squared is equal to P squared. And when I first got P squared dividing A squared, I got P squared dividing B squared based upon what we were given with the GCD of A and B being P. And by definition of GCD, P divides A and P divides B. Okay? But what I want to show here is that basically that P squared, so therefore P squared is a common, let's write words down that I said, divisor of A squared and B squared. Okay? But now we've got to talk about it being smaller. So here's the deal. So as P divides A and P divides B, just a little practice on you guys on your definitions, then by definition of divides, there exists integers, pick my favorite guys, x and y, such that, again, it's always about equations. A equals px and B equals p times y. Okay? Also, this implies a squared is equal to p squared times x squared, and b squared is equal to p squared times y squared. I just squared both sides, and when you square integers, it doesn't matter about the integers at all. Okay? So, let's keep going here. Now, here we go. So, I've got p squared as a common divisor. The greatest common divisor, I got to make sure that p squared is going to be the biggest guy of all. So I'm going to assume that there is a smaller common divisor. I'm going to call him Q. Okay? So let Q be a divisor of the a squared and the b squared. Okay? In the sense that Q is actually equal to the GCD of a squared and b squared. Okay? So I'm going to figure out Q is give myself the actual GCD of a squared and b squared. Now, by theorem 1.2, there exists integers, call them u and v this time, such that you get your equation. Q is equal to a squared times u plus b squared times v. Okay? But by substitution, Q would be equal to a squared was equal to p squared x. P squared x times u plus b squared was equal to p squared y squared. So a squared was equal to p squared x squared, and then that times u, plus b squared was equal to p squared y squared times v. And you notice you have in common here that the p squareds are in common. Well, that will imply that q is equal to p squared times x squared u plus y squared v. Well, since x, u, y, and v are integers, then x squared u plus y squared v is an integer. So by definition of divides, p squared actually divides q. So the greatest common divisor, okay, but p squared actually divides q, which actually implies that the GCD of that a squared and b squared must be equal to p squared. So my idea is right now, this is not a formal proof or anything. This is more, I kind of want to show you this idea of the want to show page on this particular material and stuff, and trying to formulate ideas and the like. So I'm really big into this want to show page, but this is stuff I never actually show professors when I'm writing up a proof. I basically am connecting the dots and writing down my answers and the like in terms of how things fit together and stuff. The other problem I wanted to focus on is the next problem up, which is problem number 18 out of your book. So with problem number 18, we have this. It's this idea of prove or disprove. Prove or disprove the following statements. A, if P is prime and P divides A squared plus B squared, then P divides C squared plus D squared, then P divides A squared minus C squared. And B, if P is prime and P divides A squared plus B squared, and P divides C squared plus D squared, is that true that P divides A squared plus D squared? A squared plus C squared. And C, if P is prime and P divides A and B, and P divides A squared plus B squared, then does P divide B? So it's kind of a three-part problem here, but it's a question whether it's true or false. And how do you prove something is false? So again, this is problem number 18. So copy this thing down here. Problem number 18, and I will start off and I'll restate the problem. This is actually part A. If P is prime and P divides A squared plus B squared, and P divides C squared plus D squared, then is it true that P divides A squared plus C squared? And that's pretty much a question mark here. So this is our problem number 18 with this stuff. Now, with this, what's your feelings on this? Well, honestly, when you start adding some things together, P divides a thing that's being added. Does that force that P is going to divide, a combination of the things that are being added here? And my feeling is no. And so, with no, what you really want to show is a counter example. If it is not true, you cannot prove it. All you have to do is a counterexample. A counterexample is actually when you start throwing numbers at these things, and so you come up with numbers. So for this one, and this is, you have to kind of state this here. All right, you give yourself a prime. Given 13 is prime. Okay, so there's my figure. Start off with that one. And here, I'm going to I'm going to give myself some letters here. A. I'm going to let A be equal to 2. I'm going to let B be equal to 3. I had to come up with these numbers before. I'm going to let C be equal to 5. And I'm going to let D be equal to 12. And now I'm going to show that it doesn't work. Clearly, P13, this is my P, P13 is prime. Okay? And I want to show you that P divides A squared plus B squared as 13 divides A, which is 2 squared, plus B, which is 3 squared. Now, 2 squared is 4, 3 squared is 9, 4 9 is actually 13, and clearly 13 divides 13. So, this is true. Also, P divides C squared plus D squared. P, again, is 13. That divides C, which is 5 squared, plus D, which is 12, and we're squaring it. 5 squared is 25, 12 squared is 144, 25, 144 is 169. and which is actually 13 squared. So 13 divides 169, 13 squared. So again, this is true. But here comes my contradiction. But I'm going to show you that P does not divide A squared plus B squared. A squared plus C squared would be equal to A was 2, 2 squared, plus C, which is 5 squared. 2 squared is 4. 5 squared is 25. That's equal to 29. And 13 does not divide 29. And there is my counter example. So this thing is actually false. Okay? Let's take a look at part B. Part B on this particular problem stated that, quote, I actually did part A there. I can do the same thing. This is actually part B. And part A, so if I look at this thing as I'm looking at the problems here, I'm going to do the exact same thing. This one was I'm supposed to show that P divides it. Does it divide A squared minus C squared? And this one was the A squared plus C squared. So I bet I can do the exact same thing. So in the same similar situation here, I'll rewrite A over here with a minus. So if P is prime, and P divides A squared plus B squared, and P divides C squared plus D squared, then is it true that P divides, it was A squared minus C squared? That was a question mark here. And again, I'm going to use the exact same numbers on these things. So back it down just a little bit so you guys can see this. And so using again the same thing, so we're going to give ourselves, given P, I'll set equal to 13, and of course this is clearly prime. And I'm going to use the same numbers. And let A equal 2, B equal 3, C equal 5, and D equal 12. So I bet I'm going to get the same thing. But you have to state it. You have not just throw numbers at me, you have to show me. So P divides A squared plus B squared. Yep. That implies that 13 divides the 2 squared plus 3 squared, which is 13. That checks. And P divides C squared plus D squared, because that implies that 13 divides the 5 squared plus 12 squared, which is 169, and 13 divides 169. So that one's good. But here comes my counterexample. We're focusing on, this time, A squared minus C squared. And that would be equal to the A squared is 2 squared minus the C squared, which is 5 squared. And that's 4 minus 25, which is negative 21. And again, 13 does not divide negative 21. So this is a counter example. So if you ever have to disprove anything, you have to disprove with counter examples. So I want to give you a couple examples of that. Now, the part C of this guy, so slapping this thing over, the first one was false and the second one was false. So what are the odds on the third one? I believe this one is going to be true. If P is prime and P divides A and P divides A squared and B squared, A squared plus B squared, then P, is it true that P is going to divide B? That's going to be a true statement. So I kind of want to show you something or other here. So I'm setting this thing up and kind of blowing it up a little bit more. There we go. Here I'm rewriting this problem. So this is part C. It says this. If P is prime, and P divides A, and P divides A squared plus B squared, then does P divide B? We're going to turn this into a theorem. Okay? But we have to prove it. So first off, I believe the answer is yes. And this, I'm going to use this as my scrap sheet of paper. Because I want to talk about ideas on this thing first. So ideas of why this is true. And then you go and write it for me. I never get to see this paper. These are my ideas. So P is prime. So I got all those wonderful definitions and theorems of being prime. And I'm given, so we're given P is prime and given, start off with P divides A. What does it mean for P to divide A? By definition, this is my scrap paper, by definition, so I kind of shorthand it. There exists an integer, pick one, call it x, for example, such that if A divides P, P divides A, who's bigger? A is bigger. A is equal to P times x. We're also given that P divides A squared plus B squared. Then, by definition, this is definition of divides here, there exists another integer, we'll call him y, such that, let's see here, A squared plus B squared is equal to P times y. You notice, the goal in your math proof classes is to take these definition theorems and come up with equations so we can manipulate it. I want to show that P divides B. So I'm going to kind of put these two guys' equations together. So we have here A squared plus B squared is equal to PY. I can replace A with PX, so this would be PX squared plus B squared is equal to PY. I can group all my p's on one side here, so I'm going to subtract px squared from both sides. This will give me that b squared is equal to py minus px20 squared. And when you square a couple of integers, that actually means that we have this p squared, and you can distribute the power, py minus p squared x squared. Well, what do I have in common? I got a p in common. I can factor it out. B squared equals p times y minus, factoring out the p, I'm still left with other px. Well, since y, p, and x are integers, then p divides b squared. Geez, Dr. Taylor, you're supposed to show that P divides B. You're right. But I want to remind you of some things that we've proved before. And that was at Theorem 1.5. So P divides B squared. That means that P divides B times B. And what were we given? P is prime. To quote it, but Theorem 1.5, we've actually proved that before. Theorem 1.5 says when P is prime and P divides a product, it either has to divide the first guy or the second guy. So by Theorem 1.5, P dividing B squared means that P being prime has to divide B. And we're done. Now, take a look at this guy here, and you'll notice that this is actually, like I said, my scrap sheet of paper type thing here. This is not a formal proof. You turn this thing in, you're going to lose so many points on structure and stuff. It's a writing intensive class. So, that being the case, I want to go back and rewrite this using my scrap sheet of paper with the formal way it should be written. So let me rewrite this guy for you guys. So, here we go. And I'm going to write down the question again. That's a theorem. This is part C. It stated this. If P is prime a squared plus b squared, then p divides b. So here's my statement that we're turning into a theorem now. So here comes the form of proof. We are given that p is prime, and p divides a. Now, in this world, you don't have to state everybody's an integer. A, B, C, D, E, F, and G are all integers. It's implied in the chapter, so you don't have to go out of your way to do that. But so just use the letters and understand these are all integers in this chapter. So, given that p is prime and p divides a, then write it up. Then, by definition of divides, tell me which definition, because we have lots of definitions out there. By definition of divides, there exists an integer x such that you have to state him who he is before you get to use him. I want equations. So if p divides a is bigger, such that a is equal to p times x. Okay. Also given p divides a squared plus b squared. Again, by definition of divides, there exists an integer y such that a squared plus b squared is equal to p times y. Okay? Statement and reason. Now I'm going to put the two equations together. So as to recall the equation, a squared plus b squared is equal to py. Then I'm going to go ahead and solve this thing for b squared. Then b squared is equal to py minus a squared by subtraction. Statement, reason. All right, now let's keep going. Thus, b squared is equal to py minus, I get to replace the a with px, but it's being squared. This is by substitution. Hence, great linking words. Thus, therefore, hence, this implies. Hence, b squared is equal to py minus p squared times x squared. Okay. By algebra. It's a great word. We'll get more deep algebra questions later. Okay. But all I did was just square both terms. This implies, if you write this in paragraph form for proper proof, notice I'm not using any symbols, just equations here. This implies that b squared is equal to p times y minus p, pull out one of the p's there, p x by factoring. If you know the algebra that you did, if you said by algebra, I would accept it, but we actually factored out the p. Well, now here comes that back stating the definition. Well, since y, p, and x are integers, and sums, products, and differences of integers are still an integer, then y minus px is an integer. Okay? Therefore, this guy's an integer. B squared equals p times an integer. Therefore, by definition of divides. No abbreviation on the stuff. Definition of divides. P divides b squared. B squared by definition is b times b, and since p is prime, thus by theorem 1.5, p divides b. The last statement of your proof should always be a statement of what you're trying to show. P divides b. When p divides a product of p's prime, it's either got to divide the first guy or the second guy. B squared is b times b, so b has to divide b. So there is the actual write-up from the scrap work that I did. I never see this. I want to see the written up, writing intensive, perfect part of my paper proof and stuff. So this is the proof of that particular statement. Okay? Now one last thing before I let you guys go. I've just posted your first homework set to turn in. And so I kind of want to show you where this is located at and stuff. So see if I can mess up my screen over here. This is very sensitive with the little mouse thing here. So here is our Canvas page. And if you go under modules, you'll see over here, these are my videos. This video will post right down here. And there is your first homework set. So when I click on this guy, it's going to take you here. And you click on the little link that I gave you here, and there's a submit button. So what you're going to do is you're going to click on this guy, and you can open it up, and it will open up, and you want to print this thing out, and you're going to, these are some problems out of the textbook that I typed up for you guys. I want you to write up the proofs of these guys in the elegant form, no symbols, writing intensive stuff. And there's one, come up with a prove or come up with a counter example on something like this. So you kind of want to play with it and stuff. Stated it just the way the book did. And here's a classic one right here, given the GCD of A, B is 1, so A and B are relatively prime, and both A and B divide C. I want you to prove that A times B is going to divide C. So there's only 4 problems on this thing. So I've given you a couple of days to turn this thing in. So, but what I want you to do is, after you've written this stuff up, you need to scan it as a single PDF file, a single file. And then you're going to come over here and submit. And when you click on submit, you'll get a way to actually browse and upload this thing, and it takes it to Canvas. And from there, we'll actually copy it out and get it graded and stuff like that for you guys. So I hope this video has been helpful. I hope all the videos have been helpful on these interesting days that we live, making you guys have to watch videos to learn this material. So study hard and start working on this homework set. So see you later.